So, hello everyone, welcome to another session of Coffee O'Clock. And I'm your host Akash Kundu, a PhD student at Institute of Theoretical and Applied Informatics, Polish Academy of Science. So once again, to give an intro to the structure of the session, in first 30 to 45 minutes, our guest speaker gives a talk about a specific topic in quantum, which is followed by 10 to 15 minutes of Q&A session. And afterwards, we do a casual discussion related to the topic, or maybe closely related to the topic, not actually related. So before directly proceeding to the talk, which is about quantum error correction and Clifford group, let me introduce to our guest speaker, Dr. Devika Sharma. She completed her master's from IIT Bombay, and she was an Institute Silver Medalist. And she pursued her Doctor of Philosophy from TIFR, Mumbai, and she conducted theoretical research work in deformation theory of Galois representation, modular forms, and elliptical curves. And currently, she is a postdoctoral fellow at the Weizmann Institute of Science in Israel, and she is working in post-quantum lattice-based cryptography and also quantum computing. So we are very much privileged to have Dr. Devika Sharma with us. So Devika, the floor is all yours, and please start your presentation.
Thank you, Akash. Thank you, Rishi, for organizing all of this. And also, I think I want to thank Rajiv, who's probably not here because he told me that he was traveling, but he will try to come. I don't know where he is, for initiating it. Thank you, Akash, for my introduction. Well, I finally come to quantum error correction after studying math and really abstract elliptic curves and modular forms. And then I moved to, he gave a very good introduction. I'm just trying to tell you that it was a bit of hopping here and there, finally to arrive to where I am right now. So starting from elliptic curves, which was hardcore mathematics in my PhD thesis, I moved to a computer science group here, which does both, like Akash mentioned, post-quantum cryptography and quantum computing. And so with them, initially, I was still using some math. Lattice-based cryptography has some involved number fields and orders and things like that, and also Galois representations to some extent. But now quantum computing has gone down to very basic linear algebra on one hand, but error correction is too complicated. There are way too many variables to control. So today the talk is, as you can see the title on the slide, is Quantum Error Correction in the Clifford group. It's very basic group theory and linear algebra. We will begin with just brushing up basics of quantum computing, just to be on the same page, all of us. And then I will describe why quantum error correction is needed and how do we do it with an example. And in the meantime, I will show you here and there how the Clifford group basically is. It's always present. It's an elephant in the room, where if you address it, then it works to your advantage, but it's always present. So this is how it's going to be, and let's begin with the mathematics of it all. Thankfully, I think this is a small group. We are, 10 people? So you can ask me questions, and I will try to answer them, although I know a little bit of here and there, but let's see. I will try to answer them to the best of my capabilities. Okay, so just for a brief introduction, we all know qubits. The first qubits that we are introduced to is the 0 and the 1 state. Yeah. I want to activate my marker so it will become easier. So this is the first qubits that we are introduced to. They live in a Hilbert space, which is the space of qubits that look like this. It's a linear combination of 0 and 1, where the coefficients are allowed to be complex numbers, but they have to be on the sphere. Okay. What can you do with a generic qubit? You can either do nothing, which is the identity gate, or you can bit flip it, which means that you can switch between 0 and 1, and your output would look like alpha 1 plus beta 0. This is called the X gate. I think there's a flipped classroom, right, that describes all of this to people. So, okay, I will go quickly then.
Yeah.
And another thing you can do with a generic qubit like this is a phase flip, which is just adding a -1 in front of the coefficient of 1. This is called the Z gate. And together with the X gate and the Z gate, you can generate a group. How do you generate a group? You basically take combinations of these. You will take X square, which already becomes identity because flipping a bit once and then flipping it back is identity. So this is an order 2 group, order 2 element. And similarly, Z is an order 2 element. So when you generate the group using these two generators, you will end up with identity XZ and the product XZ. Okay, but you're also allowing coefficients. I'm gonna just say the coefficients ±1 and ± identity. So all of this together is called the Pauli group. Okay. Another, well, you don't just stop here. You can also go ahead and do the famous Hadamard operation on the qubit. It would take the 0 qubit to the plus state, 1 to the minus state. You can further do the phase gate and also the C0 gate, which is very similar to the classical XOR gate. What you do is it's a 2 qubit gate and you just add to the second qubit whatever the value of the first qubit was. All right. So it's very interesting how you only are studying 3 gates, but somehow they managed to generate this elephant, which is very useful. It's called the Clifford group. Okay, so the group generated by the Hadamard gate, the phase gate, and C0 is called the Clifford group. And originally, the definition of this group is given as the set of all unitaries that when you act by conjugation onto the Paulis, you will stay inside a Pauli. For instance, just to give you an example, if your Clifford gate is the Hadamard, you apply it to X, and then you conjugate, you get the Z gate. Okay? And both of these are Paulis. So this is the definition of the Clifford gate. All right. An interesting theorem of the Clifford gate and also very useful is the fact that just these 4 gates, the 3 gates from the Clifford, Hadamard, phase, and C0, along with the Toffoli gate, will be the set of all universal gates, which basically means that whatever action you can do on qubits, you can approximate it using just the combination of these 4 gates, 3 coming from Clifford and the Toffoli gate.
So, Devika,
Yeah.
you said that in the group, in the Pauli group, it's X, Z, and XZ, right? But would the order of multiplication also matter, like XZ and ZX?
XZ and ZX are, they just differ by a minus sign. No, you're allowed to do that. So if you're, where did I write that? Sorry, I'm going to go back to where I wrote the Pauli group.
Yeah.
Here. So this set already will contain ZX is just minus XZ.
Okay,
so
and that's when you got the ±1 and ±I. Aha, okay, yeah, thanks.
All right. Okay, so this forms the universal set of gates. And group theoretically, what have we learned so far? We have these 4 groups, beginning with just the identity, which is you do nothing on your qubits. Then you can do the Pauli operations on your qubits, which is either bit flip or phase flip. And further going on, you can do Clifford operations on your qubits, which is either Hadamard or the phase gate or C0. And if you just add 1 Toffoli, as shown above, you can basically do any unitary operation on your qubit. Okay. This is just the basics of, this was 101 quantum computing for 2 classes in less than 5 minutes. Okay. An interesting thing right now is I'm pretty sure all of you are quite aware, and also on the Discord channel we keep posting, not me, other people keep posting what's happening in the world. So I'm pretty sure all of you have heard this, the term before, the era that we are in with respect to quantum technologies is called the NISQ era. I think John Preskill coined it, and I see lots of nodding heads, so I didn't know this. I recently found that. And it appropriately describes where we are right now. So what does NISQ stand for? N is noisy, I is intermediate scale. Sorry, I and S both together, and Q is always quantum, also in Q India, I think. So we are in the NISQ era. What does it basically mean? What noisy means that the quantum processors that we have right now are sensitive to the environment, and when they interact with the environment, they lose their quantumness. Okay? So this is the noise part, and this is what error correction tries to correct. It doesn't try to control it, it lets it happen and then it corrects it. Okay, so that's the noisy part. Why are we calling it intermediate scale? Again, because right now the quantum processors are as big as containing 50 to a few hundred qubits. So we hope that in the future, which will not be intermediate, but it would be like the final phase would have at least a few million qubits. Okay, and so again, intermediate is both a combination of the fact that we don't have a lot of qubits, and we also don't have ideal gate fidelity. It's moderate. Okay. And finally, so all in all, NISQ basically means that we are advanced. I mean, we've begun the advancement, but the advancement is not enough to reach any sort of fault-tolerant computing that you can do with your processors. And it's also not large enough, so you can take advantage of quantum supremacy. Okay, so this is for how we would intuitively describe the NISQ era. And when would we say that we've passed this road? It's not a roadblock, it's like on the way. And when would we say that we've passed this stage? They say that if we will manage to run Shaw's algorithm, which popularly is known to break RSA and hence all the encryption that we know right now, when we manage to make a quantum processor that can successfully run Shaw's algorithm, we will say that we've arrived. Okay, so that would be after NISQ. And how do we intend to get there? There are two ways, and that's what the world is doing right now. They're trying to increase the number of qubits on one hand, and also at the same time reduce the error that's happening in the gates and the hardware. And together with these two, hopefully we will manage to control and basically accelerate how efficiently a quantum machine will work. In this talk, we will focus on the first part of how will we correct errors in case they were to occur. An interesting thing to mention here is the fact that in my head, error correction is not like the Zeno's paradox. Are you guys aware of the Zeno's paradox? Not really? Okay. So Zeno's paradox is interesting. It says that you're a person standing at 0. You're supposed to reach 1, which is probably what we're calling, at 0 we are at the NISQ era, and 1 will be when we would have arrived with quantum technology. So the rules to reach at 1 is at a given time, you can only cover half of the distance left. So if you're standing at 0, you go to half. At half, you can only go to 1/4. At 1/4, you can only go to 1/8. So you're adding like 1, at the nth step, you're adding 1/2 to the n every time. So if you keep doing it, you will never reach 1. Okay, this is mathematics, I don't know, calculus 101 as well. But thankfully, error correction is not like Zeno's paradox. You don't have to go all the way to 1 to reach an ideal gate which will work ideally and have 0 error happening. Even if you manage to reach some threshold, we have codes in place where you can do fault-tolerant computing using that. And this is called the Threshold Theorem. It says that if your hardware creates noise, which is I think right now they say which is 1/10 to the 4, between 1/10 to the 2 to 1/10 to the 4. If your hardware has that level of noise, then you can easily do fault-tolerant computation on it. Okay. All right. So a lot of philosophy, and let's see what actually noise means. So the idea is that you have an initial qubit and you have a quantum channel, which I'm going to denote by this line. And you want this qubit to travel the quantum channel and reach on the other side. And your hope is that the information will be passed correctly. You don't want it to become something else in the...
Devika, can you also say what a quantum channel is? Maybe not everyone is familiar with.
I am just very roughly using the word quantum channel. It just basically means that it's a circuit, basically. I have a qubit, I'm gonna run some circuit on it, and at the end of it, I will have something, and I'm hoping that whatever I have at the end will be exactly this, and nothing in the middle will somehow ruin the input that I had, okay? This is one way of understanding it. Another is, suppose I was Alice. It will come up again in a few minutes. I am Alice and I want to send a message to Bob. And I don't know, just assume a scenario where a quantum information can travel. I want to send a 0 qubit to Bob. And I don't want this qubit to become 1 on the way.
Right.
Okay, so this is what I mean when I say a quantum channel. But what is happening right now is all the channels that we have interacts in the middle with some environment, and there's a noise. Okay. And so what do we want to do? We are coming to terms with the fact that right now we have noise. We can't do anything about it. So what can we do with whatever output that I get, which I'm assuming is not exactly what Alice wanted to send me? And the point is that how do I recover the original information that Alice wanted to send me? And this is the basic idea of error correction. So you input your ideal input, whatever it is, but then you encounter noise on the way. You assume there was noise and you found something at the end of it. But now how do you recover the right information from this noise, from this noisy output? And so how do we do this? We begin with the initial qubit that we have. This is a very simple example, and I think it's very easily understandable as well. So if you have any questions, please ask. So we have a qubit. We begin, and the hope is that I will send this qubit along the channel, and in the end, whatever I recover will be close to the initial state. Okay. Really philosophizing it if you want. This is my cat. Schrodinger's cat, not mine. I'm sending it across, and I'm hoping that if the cat was alive to begin with, then the channel will not kill it on the way. It might get a little unconscious on the way, but it should not die. Okay, so that's the idea. And how do we do this? We take the cue from classical error correction, where we have one qubit, we add a few extra qubits to it, we encode the whole thing into a block, and then this block can interact with the environment and get all ruined on the way. But then I should have a recovery procedure in place so I can recover the original information that I had after this recovery point. And again, like I said before, hope that whatever I have got is close to the initial state, or at least do it with very high probability. Okay. This is the idea behind quantum error correction. Okay. Like you can see right now, I had one qubit, but I added 4 extra to it. So I mean, we are already in a place where we don't have a lot of resources at hand. We just saw that we have about 50 to 100 qubits. So why are we wasting resources when we don't have it? We justified that the use of more resources as follows. So the idea is that you add these extra qubits. So somehow what you had originally, your original information in the original qubit sort of gets spread over the new qubits that you've added. You encode that information. So you're basically spreading out the error that might happen. It's like if someone completely breaks one qubit, the hope would be that this information in the other qubits will not it's like if you break something with a hammer on one, the other ones will remain intact. Okay, so that's the hope. And also at the same time, the fact that you are spreading it out will also lower the probability of error that will occur. This, I think, the fact that you can justify that the probability decreases is a very cool exercise. And maybe I can post it on the chat later, or we can talk about it after the talk, but I just want to mention it here. So it says, what I mean right now is that suppose the probability of error was some capital P to begin with. If I only had one qubit, then encoding it into lots of them, I will manage to make the probability of error in, okay, just going to say the order of P square, which is already better. Like if I had a system that had error 1 upon 10, then I'm already increasing it to 1 upon 100, which gets me closer to the threshold that I told you about earlier. So this is why we want to use more resources, but they work out to our advantage. Okay, let's see with an example what I mean. This was again a lot of philosophy. So what's happening here, I'm just going to very briefly describe the 3-qubit repetition code, which will also give you an idea of the stabilizer code. And again, it will tell you how the elephant called the Clifford gate is omnipresent. Yeah. So just for simplicity, I'm going to do the 3-qubit code, and it corrects 1 bit flip error. Okay, I will tell you what that means as well. So what's happening here? What's the setup? There's an Alice who has this information, who has 1 qubit, and which is alpha 0 plus beta 1, and she wants to send it to Bob. Okay? But the channel that they're using to transfer the qubit is noisy. Again, for simplicity, we are assuming that the noise in the channel only makes one error. So remember I told you that you can encode, you don't have to send just one thing, you can send, add some ancilla on the way. But whatever ancilla I will add, the channel is promising that it will only ruin one of the qubits in the encoding. All right, so this is the setup, and Alice begins. Remember that in error correction, the steps are you have information, you're going to encode it, assume that error occurs. So this is what Alice will do. She will have the information and she will encode it. Now Alice's job is over and the qubit has gone. Bob assumes qubit had noise on the way and he wants to do some experiment to find out where the noise occurred on the way, and then establish a recovery procedure, and then get the output, apply the recovery procedure to the output, and then have the information intact that Alice wanted to send. Okay, so this is how. So let's first do encoding. The second step would be detection of error. We will see what that is. And the final step would be recovery. We will see all of them. So encoding this is a 3-qubit code. So I'm encoding 1 qubit into a Hilbert space of 3 qubits. So this is a Hilbert space of dimension 8, 2 to the 3. And we will encode alpha 0 plus beta 1 as alpha 0, 0, 0 plus beta 1, 1, 1. I want to ask at this point, can anyone tell me how would they do it? Just whatever comes to your mind. What are the unitary operations that you would apply to alpha 0 plus beta 1 and 0, 0 to make it into alpha 0, 0?
Can I say? I mean, I already know.
Oh, yeah, okay. Yeah. Good.
Okay. So it would be Hadamard and C knots.
Exactly. So I am not, everyone will go back to Gaurav and ask him what he meant by Hadamard and C naught. I mean, how will he do it? I just want to point out that he used the word Hadamard and C naught. Both of them are Clifford gates. So the fact that you're using Clifford gates in encoding is the first place where Cliffords show up. Okay. So for encoding, you're using Cliffords. Do other people want to see this, how this works? Because it's quite simple. Yeah.
Yes, please. Yeah.
Okay, so I'm going to do it very quickly. I have this. And wait, I'm not applying a Hadamard, Gaurav, this way.
Right. It's only C notes. I'm sorry. Yeah.
I'm only doing a C naught. I will do a C naught with a control will be the first qubit, and I'm applying it to the second qubit right now. Gaurav knows a bit too much. He's talking about the 9 qubit game, right? So when I apply C naught on the second qubit here with the first qubit as control, what's going to happen? This will become alpha 0 0 plus beta 1 1, and I will still have a 0 here. And then I do the same thing, C naught with the first qubit, or I can also do it with the second qubit, apply it on the third one, and I'm going to arrive to exactly this state phi. Yeah. So I use 2 C naughts. They are both Cliffords. Just keep in your mind that encoding needs the Clifford gates. All right. So Alice has encoded. That's why her job is over. She sends the qubit forth in the noisy channel. The qubit encounters this noise here, and this is where Bob begins his. This is where he begins his action. So he's going to first see what error occurred. And this is what we called syndrome. I'm going to call it syndrome collection because I'm collecting information to decide which error occurred on the qubit that was sent. And how do we do this? So recall again that this quantum channel promised that there will only be one noise on the way. So suppose the noise occurred here. And I'm sorry I didn't describe. I did. I said that it will only correct one bit flip. So what does that mean? It means that there can only be one bit flip here, which is that if the bit coming from here, if qubit coming from here was a 0, it passes and becomes a 1. So my psi, which is alpha 0 0 0 plus beta 1 1 1, when it reaches here, it has become alpha 1 0 0 plus beta 0 1 1, right? Okay. And now Bob needs to do something to know that it has become that a bit flip has happened on the first qubit. So what is he going to do? He will do he will add 2 ancilla qubits 0 0. Okay. And then he'll do a C naught with the first qubit on the 0, followed by a C naught on his first qubit with the second qubit here. So let's see what's happening. I'm going to change. So we are assuming that an error occurred here. And what happened here to the state? It became alpha 1 0 0 plus beta 0 1 1. And when Bob does his detection experiment on the first qubit, what's going to happen here? The 0 with the C naught, there's a 1 here. So the 0 will flip once. And then there's a 0 on the second one, so it will not flip. So you will end up with a 1 at the end. Okay, so a flip has happened here. On the second one, it will do another flip here because the first one is 1. And then the second one is 0 again, so it will not do anything, and you will end up with a 1. Okay, so now your syndrome is 1 1, which means that the first qubit is different than the second and the third, which means that error occurred on the first qubit flipped. Let's see what happens on the other one. So, okay, just going back to the first thing. Suppose it all remains as 0 0, then it's easy to see that nothing happened because it means that all 3 of them were the same, right? Because if these 2 are the same, they don't flip 0. Or they flip 0 twice if it's a 1 1. If 1 and the third one is the same, again, they don't flip the second one at all. So if your syndrome measurement is 0 0, then there's no error. If your syndrome measurement is 1 0, which means that on the first ancilla, it flipped once, but on the second, it didn't flip. So if on the second it didn't flip, it means that the first qubit and the third qubit are the same. But if it flipped on the first one, it means that the first and the second qubit are different. And hence it means that an error on the second qubit happened. So second qubit flipped. And similarly, again, by exclusion principle, this is where the third qubit will flip. Okay. And now Bob has all the information just by doing these two measurements. He knows what happened with the error on the in the erroneous quantum channel, and he does the exact correction. If he sees 1, 0, then he flips back the second qubit that he got, and he recovers the psi that Alice wanted to send. Okay, this is the first example of a stabilizer code or a repetition code. Why are we calling it a repetition code? Because you're repeating the information. You embedded it into 3 qubits, even though the information was a 1 qubit. Okay, and why are you calling it stabilizer codes? It will involve some math description of how you can basically describe the encoding and the error occurrence and the detection using just the Pauli and the Clifford gates. Okay. What I want to point out, yeah, sorry, there's a question.
No, yeah. So I was just saying, so here the key component is that the noise channel only includes 1 bit flip, right?
Exactly. For
So
simplicity.
But yeah, but if it had like 2, 3, then if we increase the number of repetitions, then we should be able to figure that out. Or
you can, okay, so I'll say it. Remember, I wrote down that this is an exercise that you can show how the probability improves if you do repetition. So the probability of what I just wrote was the probability of 1 error occurring. You can improve the probability of 1 error occurring by p square. The probability of 2 errors occurring would also be p square. We can talk about this exercise after the talk if you want. But the probability of 3 errors occurring, which means that 0, 0, 0 will become 1, 1, 1. That is already order of p cube. So that I can ignore. Okay. We're only worried about, but we see here that 2 errors occurring is the same probability as 1 error occurring. Okay. So those we can correct with more repetitions.
okay. So this p square, and the p square is for this 3-bit stabilizer code. Or
Yeah. P square is the 3-bit stabilizer.
Okay, thanks. And there are some questions in the chat. Would you take this later, or
Are they if they're relevant to this part, then yes.
so the question is the circuit for syndrome collection dependent on the problem?
Yes, definitely.
Okay.
Yeah, whatever detection you will design here will depend on what your circuit, what kind of errors you are dealing with. Okay.
And the encoding you use, right?
And the encoding as well. Yes, that's right. So yes, this will be encoding, will depend on encoding plus errors.
Hi. The circuit for this syndrome collection is just applicable to this problem, right? It cannot be applied to some other problem.
You can't blindly take it away. You will have to check if this works in the other problem as well. But
before designing this, we have to know the input. Is that what it is?
Sorry for?
In order to design the syndrome collection, do we have to know what the input is?
You have to know what the encoding to the input is. If you know how you're encoding the input, then you can design your syndrome collection.
Okay. I didn't quite get it, but
yeah, because
maybe
here also you don't need to know what alpha and beta are, right? You just need to know that. I mean, if you need to know your input, then you have to know what alpha and beta are. But in this, alpha and beta doesn't really matter. It's just that you know that 0 and 1, you've put it to 0, 0, 0 and 1, 1, 1.
Yeah, so what I don't need to care about what alpha and beta are, like Rishi said. By encoding, I mean how you're putting 0 to 0, 0, 0 and 1 to 1, 1, 1. Okay, that's the encoding part. The encoding does not involve alpha and beta at all.
Yeah, maybe what I was thinking was, what if the input was 001 and 100? So in that case, this
Again, what is the
diagnosis,
input here?
yeah, what is the encoding? Maybe I'm not sure if I'm phrasing it properly. What if the input was that, which is exactly right now, like the error part, which is alpha 100 and beta 011.
Okay, so you're saying suppose Alice wanted to send alpha 100 plus beta 011 to Bob, and suppose there was an error on the way which flipped the first one and actually made it into a 00 and 111, then yes, you will have to design your circuit differently, because you will have to assume that in the beginning the first two qubits were of different parity, but now after the error they're of the same parity. So your syndrome detection should detect that the first two qubits are of different parity in your encoding.
So would it be like we would have some class of problems? So you follow this syndrome collection circuit for this class of problem, kind of like that?
I think you can do syndrome collection if you fix your encoding. Yes, there can be, you can also abstract it a bit more and say if your encoding is described by these Pauli operators, then this is how you will design your syndrome collection.
Okay, got it. Thank you.
Okay, I will, let me just add another page and give you a very cool idea of how we do this. So the idea is that this is the information that you want to send. Okay, but now it's, again, you want to save it from the noisy channel. So what you do is encode it into a bigger Hilbert space. And this encoding has to be exact, it has to be in isometry. So if it was, I don't know how to describe it. Anyway, so it has to be a copy of the original information, okay? But now this is a bigger Hilbert space. And what the errors do is they take this space to other subspaces inside the Hilbert space. Okay? And these are error subspaces. So if your information after traveling through the quantum channel has somehow landed in this subspace, then an error has occurred. What the syndrome does is it finds out which subspace your original code space went to. And once you know that it went to this one, you can, where going to this one is syndrome collection. And once you know that it has gone here, then you can recover it back through the recovery process. So this is how you design the syndrome experiment and correct errors. Okay. All right. And again, I want to just stress on where all we saw Cliffords. We saw them in encoding because we used, as Gaurav pointed out, C0, which is a Clifford gate. We also saw them in detection, which was in designing the syndrome experiment, because that was again 2 C0s. And again, decoding was also the C0 because it needed to depend on encoding and detection. Okay, so in these 3 steps, in this example, it was just this one C0 Clifford gate that was used, but Hadamard and other gates are also used. But the point is that it's these 3 places in error correction that Clifford gates are used. Okay. In the setup of stabilizer codes. All right, this is one place Cliffords are used. Another very useful use of the Clifford gates is for testing entanglement. So so basically, there's a very famous theorem called Gottesman-Nil. It says that all Clifford gates can be simulated efficiently on a classical machine. Okay, so if you want to check the entanglement, I don't know if I can call it fidelity on your hardware, then what you do is you create entanglement using Clifford gates on your quantum hardware. I think these other people, maybe Achinte and Rishi would know it much better than me. That you establish this entanglement in the quantum hardware, and then you also simulate it on the classical. And the fact that you're using Cliffords, you can do the simulation efficiently. Okay. So that's another place where Cliffords are used. And this is thanks to Gottesman-Nil. And finally, where my recent work has been is Cliffords are used in randomized benchmarking, which basically means it wants to check. Randomized benchmarking is a way of checking what is the error probability in your hardware, in your quantum machine right now. And how is that done? So you basically run Clifford gates and then you run their inverses back, and it's running a Clifford gate and running inverses should be an identity. But if there was error in your hardware, then you would not get identity. And how far away it is from identity will help you tell how much error has occurred. Okay, so that's the idea of randomized benchmarking, and this is the work that we recently did. So our results were as follows. We gave an efficient
Devika, but why are we using Cliffords for randomized benchmarking? It can be, in principle, any gate, right?
Yeah, I think it can be done. Okay, why are we doing that? Because I personally, I think it's easier to run Cliffords than run Toffoli. For instance, okay, better answer is that when you do this encoding, usually Clifford gates can be done in a transversal manner. Like if you encoded 1 qubit into 3, then if you want to apply a Hadamard on the original qubit, you will apply a local Hadamard on each one of the qubits. Okay, and if an error, so then errors here will occur locally. Okay, they will not spread. It's not that it will be the fault of your circuit that the little error that you in the machine got amplified because you put a bad circuit inside.
Okay, so
Clifford basically will let your error be localized. So
okay,
you will
that's a good takeaway. Yeah,
catch it better. So our result is very relevant to randomized benchmarking. What we do is give an efficient algorithm for if you have a Clifford circuit, when is it? Then you can check efficiently that it is identity or not. Okay, that's one result. We can do it again both in the black box and white box manner, but black box is usually far more applicable. The second result is actually the cool part of the paper. We say that you have any circuit, it's any unitary, and you want to ask these 3 questions. Is it a Clifford or a Pauli or identity? And our result says that if you have an oracle for any one of these questions, then you can answer the other 2 questions as well. So if you have an oracle that says that yes, your arbitrary unitary is an identity or not an identity, then you can also use that oracle to check if it's at least a Pauli or at least a Clifford. And this is where I will stop.